Algebra 2, how are you doing? Hopefully well. This is week 6. It is 6.1. 6.1 for this week is going to be a Algebra 2 centered lesson. We're going to go over some more little vocab, still looking at asymptotes, and now we're going to look at something called a hole in your graph. And then 6.2 is going to be a fun little history lesson. I thought I should start throwing out some cool things that I find interesting at math that we're not going to have a chance to talk about this year because of the closure. So, hey, enjoy some fun, cool stuff, all right? So look forward to 6.2. 6.1 here, we're going to start with a little vocab. An asymptote, again, we've covered this before. It's a line or a curve, a line that a curve or graph approaches, but it's never going to meet or cross. So for example, I'm just going to draw little sketches of these so we know exactly what we're talking about. Here's my coordinate plane. Let's say that we have the function f of x equals x plus 3 divided by x minus 2. Sorry, I put parentheses around there. This is a rational function. Again, we see this is a polynomial being divided by another polynomial, so these are rational functions here. This denominator, again, we look for our asymptote, our vertical asymptote for our denominator. What is going to make that 0? Because if the denominator, x minus 2, is equal to 0, that means we're dividing by 0, and that can't happen. So whatever value that makes the denominator 0, in this case, I add 2 to both sides. We're just solving for x. In this case, the value x equals 2 means that that value is going to make the denominator 0, and that can't happen, right? So I know that I would have a vertical asymptote at x equals 2. So there would be a vertical line. So here's like x equals 1, here's x equals 2. Here's my vertical line, my asymptote at x equals 2, and maybe my function looks something like this, right? We're just kind of sketching these rational functions out. Asymptote, a line that a curve or graph. It's going to get really, really, really close, but it's never going to meet or cross, all right? Here's the new thing, a hole. An input value that causes both, all right, both the numerator and the denominator of the function to be equal to 0, all right? So the difference with our asymptote, the asymptote here only, we were looking at the value that only the denominator is equal to 0, right? But now we're possibly seeing that the numerator and the denominator might be equal to 0 with a single x value. So I'm going to throw out an example real quick. Here's going to be my little sketch just so we have that off to the side. So here's my coordinate plane. And I'm going to use the function, I just made this one up, f of x equals x minus 2 divided by x plus 3 times x minus 2. See, this is where I'm kind of using these parentheses so I separate these like linear factors, right? So, looking here in my denominator, technically there would be, if you think about it, there would be like 2 asymptotes because there's 2 possible values that will make my denominator 0. If I set x plus 3 equal to 0 and solve for x, I should get an asymptote at x equals negative 3. If I set this other factor of x minus 2 equal to 0 and solve for x, I'm going to get, there should be an asymptote at x equals 2, all right? But here's the difference. If I plug in x equals negative 3 into my function, I'm going to get on the top negative 3 minus 2 divided by negative 3 plus 3 times negative 3 minus 2, all right? So that means the top is equal to negative 5, and the bottom is equal to 0 times negative 5, all right? So here, only the denominator is equal to 0, all right? So when only the denominator is equal to 0, so that this value of x equals negative 3 makes the denominator equal to 0, then I would have a vertical asymptote, all right? Let's look at this other value of x equals negative 2. If I plug in x equals negative 2 into this function here, I'm going to get negative 2 minus 2 divided, or I'm sorry, it's a positive 2. It's a positive 2. If I plug in x equals positive 2 in there, I'm going to get 2 minus 2 divided by 2 plus 3 times 2 minus 2. And if I simplify that down, the top is 0, the bottom is 5 times 0, right, which is just going to be 0. So here I see a 0 in the numerator and a 0 in the denominator. So the difference between my x equals negative 3 and my x equals 2, this value of x equals 2 makes the denominator and the numerator both equal to 0. Therefore, the value of x equals 2, we're going to consider that a whole in our graph and not an asymptote. So since we have the denominator equal to 0 and the numerator is equal to 0, when I plug in the value of x equals 2, that means that we're going to have a whole in our graph at the value x equals 2. So if I had to sketch this out, I'm going to show you this on Desmos here as well. If I had to sketch this out with the information that we just found, that means I'm going to have a vertical asymptote at x equals negative 3. So I'm going to come over here at x equals negative 3 and add a little dotted line vertical asymptote. And I'm also going to have a whole at wherever the function is has an input of 2, right? So here's a sketch of my graph. Again, it's rational. It's probably going to look something like this. And then my function, it goes and it goes and it goes, and then it hits that value wherever x equals 2, and I have a hole in my graph. See how I'm putting an open circle? And then it continues on, all right? So on Desmos, this is what it's going to look like, all right? So I've got my function graphed in red. All right, my function is graphed in red. We see that vertical asymptote. I'm toggling it on and off right now at x equals negative 3. The other value that we talked about was, well, what happens when x equals 2? There should be a hole in our function. It looks continuous. Well, come on, function. There it goes. If I take this point and I'm going to drag it, ignore that 0, 0.33. There it is. See that point of 2? I'm holding it right now. That point, oh, there it is. When x equals 2, my function is undefined and it has an open dot, therefore signifying a hole in my graph, all right? So since that since the x minus 2 and the x minus 2 is on the numerator and the denominator, then that means we're going to have a hole in our graph, all right? So let's look at a couple more examples. Okay, so here is my next example. I have a function, and I've written it 2 different ways, all right, because it's technically the same thing. If you look at this one here, I have polynomials on the top and the bottom. Therefore, this f of x that I have right here, written 2 different ways, it's a rational function. And what I've done to these polynomials here is I have just factored them both out so I can see these linear factors on the top and the bottom, right? Because that's what's the interesting part, and that's what's going to tell us where our vertical asymptotes or holes in the function are going to be, all right? So once I've factored this, I get this here, and then we can look at the denominator, all right? Again, the denominator is the exciting part, right? That tells us where is this function going to have a problem, right? And I can see that this function is going to have problems with this value here, or with this factor and with this factor here. So this factor of x minus 3, well, if that's equal to 0, that's going to be essentially divided by 0, and that can't happen, right? So again, I'm setting this linear factor of x minus 3 equal to 0. Then I can solve for x by just adding 3 to both sides. X equals 3. On this other side here, x minus 5, again, that's also in the denominator, so I have to set it equal to 0 and solve for x. Add 5 to both sides, and I get x equals 5, all right? So then I say, are these holes or are they going to be vertical asymptotes? Which one, which one? Let's look at the value x equals 3, and let's just plug it into the function, all right? So if I plug the value x equals 3 into the function, I'm going to get 3 minus 3 times 3 plus 2 divided by 3 minus 3 times 3 minus 5. Okay, and then that is going to give us on the top, that's 0 times 5 divided by 0 times negative 2. Well, that's just going to be 0 over 0, right? So the value of x equals 3 makes both the numerator and the denominator equal to 0. Therefore, there has to be a hole in the graph. So I'm going to write this at the bottom. There has to be a hole in the graph at the value x equals 3, all right? And I can see that very easily just by looking at the function, because there's an x minus 3 and an x minus 3 on the top and the bottom. So I kind of already know, without having to do all this work here, I already know that there's going to be a hole in the graph, because putting in 3 into the top and the bottom is going to automatically give us a hole, all right? It's going to give us 0 on the top and the bottom. Let's just check. Again, we're just going to do the math together. Let's check the value of x equals 5. Plugging that into my function, I'm going to get 5 minus 3 times 5 plus 2 divided by 5 minus 3 times 5 minus 5. All right, and then the top is going to give us 2 times 7 divided by 2 times 0, and then that just simplifies down to 14 over 0. Since the value x equals 5 only makes the denominator 0 here, now I can say that this would have a vertical asymptote at x equals 5. So here would be a vertical asymptote at x equals 5. I'm going to show this to you on Desmos as well, but I'm just going to give a sketch of the graph off to the side. All right. Stop. Okay. So from this information, I know I have a hole in the graph at x equals 3. So let me get a different, I'll use orange. So 1, 2, 3. So here at x equals 3, there should, oh, not a vertical asymptote, a hole. And then at x equals 5, 1, 2, 3, 4, 5, there would be a vertical asymptote. So here's my asymptote at x equals 5. Maybe my function looks something like this. As soon as it hits 3, though, it has a hole in the graph, all right? It is not defined at that point. Let's take a look at what this looks like on Desmos. Here I have my function graphed in green, and I know we just decided that there was a vertical asymptote at x equals 5, so there is my line. I'm going to put that on and off so you see exactly where that is, all right? So there's my vertical asymptote at x equals 5. And since we have these like factors of x minus 3 and x minus 3 on the top and the bottom, that should mean that there is a hole at the function where, come on, stop it. There it is. Wherever x equals 3. So I'm going to go find where x equals 3 in this function, and there it is. It is undefined, all right? So there is our hole, and you see that the circle at x equals 3 for that point, it is not filled in, all right? So at x equals 3, our function is undefined because there is a hole. Okay, here is my next example. I have x squared minus 2x minus 8 divided by x squared plus x minus 2. My first step is going to be, let's see what both the numerator and the denominator factor out to be. I'm going to give you some easy polynomials. You're not going to have to use the quadratic formula on these, so don't worry, all right? So what are two numbers that multiply to be negative 8 but add to be negative 2? You can think about that for a little bit. You're going to get x minus 4 times x plus 2, all right? So this top quadratic factors out to be x minus 4 times x plus 2. On the bottom, we have what are two numbers that multiply to be negative 2 but add to be a positive 1? That would be x plus 2 times x minus 1. All right, so that's just basic factoring. I'll try and find a video if you need help with that, so I'll link that as well. There's just basic factoring here, and now we can start our little investigation into the important question, right? What's going on with the denominator? That's what we really care about. We got to check to make sure that we're not going to be dividing by 0. So I'm going to take both of these little factors and set them equal to 0 and say x plus 2 equals 0 and x minus 1 equals 0. Then I can solve. So I'm going to minus 2 from both sides, add 1 to both sides, and I get values of x equals negative 2 and x equals 1. Now I got to check these and say, are these going to be vertical asymptotes or holes in my graph, all right? So if I check this first value, again, you could plug it into the function itself and do, okay, negative 2 minus 4 times negative 2 plus 2 divided by Negative 2 plus 2 times negative 2 minus 1. You could plug it in that way. I see that this piece is going to be 0 and this piece is going to be 0. Again, I have x plus 2 on the top and the bottom. Therefore, since both the top and the bottom are 0 when x equals 2, or excuse me, when x equals negative 2, that means that this has to be a hole in my graph. So this is a hole in my graph at x equals negative 2. Let's look at the other one, all right? If I plug that into my function, let me save that arrow for later. If I plug x equals 1 into my function here, I'm going to get x, oh, I'm plugging in x, 1 minus 4 times 1 plus 2 divided by 1 plus 2 divided times 1 minus 1, all right? So here I only see that this piece is 0, all right? Since my denominator, only my denominator is equal to 0 here, that means that x equals 1 would have to be a vertical asymptote. Again, the hole in your graph, asymptote. All right, the hole in my graph only occurs when both the numerator and the denominator are equal to 0. But here, since only my denominator is equal to 0, I'm just going to have a vertical asymptote at x equals 1. Here's my last example. All right, it's a little bit different, but we can totally do it. Again, let's check to make sure that we can factor out the denominator. So the top is going to remain the same as just x plus 1. The denominator, let's see if that factors out. What are two numbers that multiply to be 2 but would add to be 3? Well, that's just a simple factoring of x plus 2 times x plus 1. All right, again, now we're looking at our denominator and saying, hey, well, what values are going to make those guys 0? Because again, our denominator, we can't be divided by 0 here, right? So I'm just going to say x plus 2 equals 0, setting both of these, x plus 1 equal to 0, set both of these equal to 0, solve for x, and I'm going to get x equals negative 2 times x equals negative 1. And then we can see really quick, if we plug in x equals negative 2 into our function, negative 2 plus 1 divided by negative 2 plus 2 times negative 2 plus 1. The only piece that is going to be equal to 0 is this part right here. Therefore, since only my denominator is equal to 0, this has to be only a vertical asymptote at x equals negative 2. On this side, however, if I plug in x equals negative 1 into this, I'm going to get negative 1 plus 1 divided by negative 1 plus 2 times negative 1 plus 1. And that gives me two pieces that would be equal to 0, right? And both these pieces are on the top and the bottom. Therefore, this value of x equals negative 1 would have to be a hole in my function, a hole in my graph at x equals negative 1. All right, so the difference between a hole and a vertical asymptote, I think I have this one graphed. I do. So again, we see this vertical asymptote. I'll type it in real quick. At x equals, what did we say, negative 2? All right, so I'm toggling that thing on and off right now. So there is our vertical asymptote. And we said that there should be a hole in our graph at x equals negative 1. So if I get a point here going, and I'm going to go try and see if I can find negative 1. Oh, there it is. So at x equals negative 1, the point is undefined, all right? There is our hole in the function. Again, we see that open dot. It is not filled in. It is not defined at that point. Wonderful, wonderful. Let me know if you have any questions. Again, today was just knowing the difference between a hole and a vertical asymptote and being able to identify these in your functions. I will give you a couple other questions that are like this, where you're going to have to factor the top and the bottom, see, plug them in, see what pieces are going to be equal to 0. Alrighty. Thank you very much. Have a great day, Rockets, and see you later. Adios.